So we've built this 3-bus machine. We started with a generic everything connected to everything machine, and then we rearranged it a bit, recognizing that we want some flexibility and freedom to allow almost anything to come into the ALU, and then the ALU result to go almost anywhere. But this allows us, or this requires us, to do some more control logic. So let's look at what that control logic looks like. Every register is gonna want any register to be able to present it to the ALU, either input. There's 2 inputs, the A input and the B input. So any register into the ALU inputs, and then we want to be able to select which inputs we're going to use to present to the ALU, and then we're going to take that result and put it back to any of the other registers. Now, putting a value to registers is easy because you just put a wire and everybody's connected to it, and then each register just chooses to load or not load what's presented at its input. But taking values from the register and putting it onto the bus is a problem. We don't want to have 2 things trying to drive the bus at the same time. You want to have exactly one thing driving the bus at the same time. And the reasons for that get into sort of the electromechanical processes of what would happen if we had one wire saying 5 volts and one wire saying 0 volts, and then the bus, which the whole point is to have as efficient a connection as possible, connected between these 2 values. Both are trying to drive 0 volts and 5 volts. The end result is a short circuit, which would melt the machine, and that would be bad. And so we want some kind of control that disconnects everything except the one we want. And so we use a tri-state buffer. This is a piece of hardware that allows it to be either 1 or 0 when it's connected, or high impedance when it's not connected. That's why it's called tri-state. 3 options, 1, 0, and then high impedance. And then we have a control point, which again is a part of that microcode instruction that says, I'm going to enable this one, and I'm going to disable all the others. So that's going to be our control logic to run this 3-bus machine, and it looks like this. So here is now the multibus machine, the 3-bus machine with the control logic added. And we'll walk through some examples of exactly how this works with our really simple assembly language. So each register can be connected to each input of the ALU. Almost. We don't need the program counter to go to both inputs because we're only ever going to add 1 to the program counter, right? Same with the instruction register. We don't need it to go everywhere, so we don't have every connection, but we could have every connection if we wanted to. Memory buffer register and the 2 data registers go to both buses, and then the ALU can do something with these things. And then the result can go back into all of these inputs, and those C's are to clock the register, right? To grab the value from the bus and store it in the register. So we have all of these possibilities that can do, again, the really simple assembly language that we've produced, and we'll see what the control points look like, what the data words look like as we build this thing out. I'll remind you of the I'll remind you of the actual assembly language that we're using in a second, but I want to sort of notate what these different control points are. And this is, again, taken from the Clements book. But the ALU now has to make some different decisions. So all of these different control points can do all sorts of different things. But in order to replicate the everything connected to everything, we need the ALU to be a bit more beefy, a bit more useful. For example, if we want to take the program counter and put it in the memory address register, it's got to go through the ALU because everything goes through the ALU. And so we have this function called copy bus B to bus A, copy bus C to bus A, right? Just pass through either B or C, those 2 input buses, to the ALU output. These are just pass it through, right? The ALU doesn't do anything, but it's still the center of everything, so it's got to decide, pass stuff through or do something. So we can copy bus B to bus A and copy bus C to bus A. Or the ALU can add or subtract 1 to B or C. Or it can add B and C together, or it can subtract them. Those are the functions that we're going to put into this ALU. And again, we put these functions in so we want the machine to be as sort of wide-reaching and variable as possible, right? In case we come back to it later and say, I want it to do a different thing, let's put some new microcode in to make it do something new. We can't change the hardware, so we have to make the ALU as versatile as possible. But with this ALU, we can do an awful lot of cool stuff, even as simple as this. So here are all of the control points. Now, this looks a lot, right? This looks complicated. But all this is a list of every single bit that can make a choice in the data path. So we've got at the very top, right? We've got two things that the memory can do. It can either read or write. And so we have a bit that tells the memory to read and a bit that tells the memory to write. And then we have a clock signal or a clock control point for each register that can read from the bus, right? And so for each register, we can tell it to read or not read. We're going to clock. We're going to capture that information or just let it pass by. These are control points. Then we have a bunch of enables that allow us to put a register onto the bus. Now, in this case, we want to make sure that only one of these is active at a time, because if two enables are onto the bus, it'll fry it. Bad things will happen. And then we have down at the bottom, we have our ALU control signals. And there's 3 control signals which provide selection of those 8 possibilities. So these are our control points, right? To set up a transfer, when we do our fetch, we want to, again, move the program counter into the memory address register. To set up that transfer, we have to allocate the control points that make that thing happen. This is our micro instruction. It is the individual bits that activate or deactivate the individual components of the machine to make that register transfer happen. And we can list them in any order. We typically list them in the order that we stack them. So this is, we will list the memory, and then we'll list the clocks, and then we'll list the enables, then the ALU. But it doesn't matter because it all happens at once. There's no ordering in a micro instruction. Everything happens at once at the next rising edge of the clock, right? So this is what we're going to build. So let's have a look. Let's have a look at what this looks like. Here is four clock cycles that do fetch, and then 3 that do execute for a store instruction. So this is going to be a walkthrough of exactly what we have to do to this machine to allow it to accomplish the instruction store into memory address M. I'm sorry, it was address before, now it's M, little things. The value that's in R0. So we'll start with the fetch, and then we will do the execute. And so each of these will be in the next videos.